Okay, then let's get started. Good afternoon, everybody. Welcome to the TrustML Young Scientist Seminar. So I'm Sugiyama. I'm chairing the seminar today. So this is actually the 40th anniversary seminar today, and we have a nice guest speaker today. So today's speaker is Shinichi Nakajima from Teiu Building. So he's also a visiting scientist at Weekend AIP. So he's our friends, basically. So today he will be talking about Monte Carlo simulation of physical systems with deep generative models. Okay, Shinichi, please start.
Yeah, thank you for the introduction. So today I'll talk about Monte Carlo simulation with deep generative models. So actually, 2.5 years ago, I visited Rican AIP Center and they gave a talk. And one of the topic was related to this. And today I will talk about some extension of that work. And for those who didn't attend my previous talk or forget everything, I will of course recap what I talked last time. So no problem. Okay. Okay. So we are working in physics applications, specifically Monte Carlo simulation in physics. So here in the right-hand side, there is a drawing of a lattice, which is which models, for example, magnetic material, where we have lattice and each grid points, we assume they are spins. And the spins follows some Boltzmann distribution defined with Hamiltonian or energy. And the Hamiltonian is typically defined like this equation. So first term is a pairwise interaction, and the second term is unary term, typically represents the interaction with external fields. And what physicists does is they use this model and they assume that the spins followed this Boltzmann distribution, and they somehow get the samples from the Boltzmann distribution, and they compute some observable O, for example, energy or absolute magnetization or something, and computes the expectation value of the observable with respect to the Boltzmann distribution. And the physicists use this tool to analyze, for example, phase transition point or and so on. And traditionally, they use Markov chain Monte Carlo method to get the samples from this Boltzmann distribution, which is unnormalized distribution. And this is a kind of established method, but there are issues like long autocorrelation and slow mixing, especially at criticality. And recently, some people, machine learners and physicists, try to cope with this problem with deep generative models. And okay, I just checked the chat.
No, sorry for that.
Okay, so in this work, we use deep generative models to sample, to get the samples from the generative models instead of applying MCMC sampling. And usually when we draw samples from generative models, we usually get independent samples, so we don't worry about the autocorrelation. And then basically we can get IID samples easily. Once we get a nice model, Q, as a deep generative model, which approximates the Boltzmann distribution. Okay, and
but I have a question. So, do you want to approximate P of S as a density function, or do you have only interest in estimating its mean?
Actually, basically, we want to compute expectation value, but actually, in the process, we need to access to the distribution. I'm not sure if I answered to your question.
Because estimation of the density is much harder than estimation of the expectation, I think.
Yes. Okay, but we basically use Q of S as the value for to apply importance sampling, but there is no physics application which directly requires the P of S itself.
Okay, thank you.
Okay, and there were several previous works, and then many people try to do this task by using GAN, RBM, VAE, and the autoregressive models and normalizing flows. And we are one of them. And but in this application, we should be careful about estimation bias, which I'll talk about in more detail. So basically, the target value we want to compute is the expectation value of O with respect to P, which is the Boltzmann distribution. And we want to use the generative model Q instead of P. And then we draw samples from Q. And then we want to compute the expectation value of O. And of course, we cannot perfectly train the model Q, which exactly matches the Boltzmann distribution. So in that case, the expectation value of the first equation with respect to Boltzmann distribution is different from the expectation value with respect to the generative model. And if there is bias, we have no tool to estimate this bias. So this is a problem which we will solve by we solved by importance sampling. So assume that we are given unnormalized true probability, which is expressed as Boltzmann distribution. And we also assume that the sampling probability is accessible. So given S, we can compute Q of S. And also we assume that the support of the model Q covers the support of the Boltzmann distribution P. Under this assumption, the target value, the expectation value of the with respect to the Boltzmann distribution can be transformed as the expectation value with respect to the generative model Q with the importance weight. Is it possible to remove? So basically, with this procedure, we can transform the expectation value to the with respect to the generative model. And here I define W, which is the ratio between P and Q. And then we estimate the target value by the importance weighted averaging, and basically this is what we want to compute. But still we have this P, which is the Boltzmann distribution, and we don't know the normalizing factor Z. So we should use P tilde, which is the unnormalized distribution here. And but we can still apply importance sampling by self-normalizing the weight. So this is the estimator we use. And here I said that the sampling probability has to be accessible. And this is not supported by all the generative models, but some of them we can do. So there are two models which provides exact normalized sampling probability, which are autoregressive networks and normalizing flows. So the first one, autoregressive model, is models the data distribution in this way. So originally it was proposed for image analysis, and let's say the X is the image, and we put some ordering for the pixels. So we have X1, X2, X3 to Xm. And in this model, we first define the probability of the first pixel. And if we compute this, we can draw the sample of the first pixel, X1. And once we sample X1, we can compute this second probability, the probability of the second pixel, and we can draw sample for the second pixel. And we continue to do this, and in the end, we get the sample of the whole X. But at the same time, we already computed each factors of the probability. So we simply multiply them, and then we get the sampling probability. So in this way, autoregressive models provide the exact normalized sampling probability. And probably more popular method is normalizing flows. So in this model, we first draw latent variable Z from some simple distribution like standard Gaussian. And this value, this latent variable is mapped into the data space X by using the bijective mapping F. And so this bijective mapping or one-to-one mapping allows us to estimate the density. And here, basically, given X, we basically just compute the corresponding latent variable Z by the inversion of F. And here we have Gaussian in the latent space. And we also need to consider the change of the volume element, which is expressed by the Jacobian. And this way, basically normalizing flows allow us to access to the normalized sampling probability. And there are some way to change, but basically autoregressive models are good, convenient for drawing discrete variable data, and the normalizing flow is good for continuous variables. And we use autoregressive models in the case of discrete variable and normalizing flows in the case of continuous variables in our applications. Okay, and this graph shows the result of the importance sampling. And actually there was previous work done by Wu et al. And they actually used autoregressive models, but they didn't apply importance sampling. So it's a very good baseline of our method. Basically, we just use the same model and they applied importance sampling, and then we get unbiased results. So here the solid curve is a reference, and I think in this case we can compute analytic solution, and our result is compatible to the exact true value, while without importance sampling there is biases and the result is not compatible. So this is the result on energy, and this is the result on absolute magnetization. And in both cases, we get compatible estimators to the reference value.
But what about the variance of the estimator?
Variance of the estimator, basically, if we do important sampling, variance increases, and then we can somehow estimate the variance by effective sample size.
Mm-hmm.
And here we draw error bars, which is too small, but basically
the sample size is large enough to
yes,
capture the variance.
yes,
the variance.
Yes. And in the latter part of my talk, I will discuss a little bit details of effective sample size.
I see.
But basically, this is physics application. So when physicists analyze some material by numerical simulation, typically they need to show the credible interval or confidence interval. And if we know the bias and the variance, we can do this. Mm-hmm. But without important sampling, there's bias, and we don't know the bias. So it's in some sense, it's not so useful. So important sampling is a must for this application. Okay, this is the recap of my previous talk. I don't know who remember it, but doesn't matter. And I want to go to the next topic, which is thermodynamic observables in lattice field theories.
Did somebody speak?
Someone has a question? Okay, so the next topic, I talk about free energy estimation in the lattice field theory. So lattice field theory is one physics research field of physics. Actually, I don't know much about this theory, but I mean, I can explain what we do. So typically, physicists assume physicists consider four-dimensional space. So one is for the time, and the three directions, the physical position. And when they apply, they work on lattice field theory, they assume the lattice structure in this time and space, time and position space. And then we have lattice like this. And we assume that each site there is continuous field. And this I write as P. And they also assume there's action, which is written as S. And for some reason, temperature is expressed by the grid size of the time, and basically they assume Boltzmann distribution in this field. And here action is used instead of the Hamiltonian, and the field corresponds to the spin in the previous application. And once we come here, then it's almost the same problem as the magnetic material analysis, and only the difference is that the phi is continuous. And by Monte Carlo simulations, physicists want to compute the path integral, which is the expectation value of some observable with respect to the Boltzmann distribution. Okay, so then this is a typical benchmark action called p to the power of force theory, and this is very much similar to the Ising model in the magnetic material analysis. So basically, we have the first term, which is the interaction term, because we have two feeds with different positions, and typically we consider them neighbors. And for physicists, this typically came from differential operator like momentum, and this differential operator basically describes the interaction between the neighboring fields. And the second and the third term corresponds to the unary term, which is governed by lambda. They are coupling constant. And then we have kappa, which is called hopping parameter. And basically this controls the interaction. And actually, we know that this system has causes phase transition at some kappa, which is around 0.26 or 7, like in this figure. And typically MC-MC sampling suffers from critical slowing down when we need to get samples around this critical point. Okay, let's move to think about free energy. So free energy is defined as the third equation, where T is the temperature and Z is the partition function of the Boltzmann distribution. And if we get free energy, we can compute several important variables like pressure and entropy. But actually estimating free energy is not as easy as other observables like energy or magnetization. And how physicists estimated free energy is like this. So we need to consider two physical systems with the actions S1 and S2. And then they draw samples from the first system, so from S1. And then we can compute the ratio between the partition function. And here, this is the estimate of the ratio between the partition functions. And here, feeds should be drawn from the first Boltzmann distribution. But if the two physical systems are very different, this value is very peaky, and then we get a very large variance. So S1 and S2 should be similar when we get this estimate with reasonably small variance. So then what we need to do is to perform numerical integration from the system for which Z is analytically computed or approximated. So this is so in this phi to the power of 4 theory, we can estimate the free energy by MC-MC sampling in the following way. So actually, if the kappa is 0, we have no interaction factor, and all the sites are independent. And in this system, actually, we can compute the partition function of free energy in an analytic form. So actually, at this point, we know the value of the partition function. And then we need to move step by step towards the target value. So that each interval we have two physical systems which are close enough. And as I told before, there's critical slowing down happens when the kappa goes through the phase transition points. And here we get a huge variance. Okay, so the right-hand side, we draw the variance of the free energy estimator. And this graph shows that the variance is quite large at around the critical point. Okay, and instead of using numerical integration with MCMC sampling, we just use the generative model, and we can actually directly compute the partition function by this estimator, which is almost like the average of the weighted importance weights. And this is actually an unbiased estimator for the partition function. And we require normalized sampling density, and the variable phi is continuous, so we use the normalizing flow. And this is the experimental result, the first experimental result where we compute the free energy at kappa is equal to 0.2. So this is actually not hard for the standard MCMC sampling, because we know the partition function at kappa equals 0, and then we should just apply numerical integration up to here, and there is no phase transition between them. So basically, this is easy example for the MCMC sampling, and then we compared the credible interval of the estimators, and here red corresponds to the Hamiltonian Monte Carlo, which is MCMC sampling with this numerical integration, and the blue shows the credible interval of the of our method with normalizing flow. So that there is difference, but the variance is in the same order, so there is no big difference. However, when we want to compute the free energy at kappa is equal to 0.3, this is a hard problem for MCMC sampling because it goes beyond the critical point. And to get reasonable variance, we increase the number of samples, and we used 14 Markov chains to reach from kappa equals 0 to 0.3, and performed numerical integration. And the right-hand side shows the result. So red is MCMC sampling, and the blue is our approach. So we see a big difference in the variance of the estimators. And we should think about the computation time for fairness, because MCMC sampling, there's no training necessary. We just apply MCMC sampling and draw many samples. So in the latter, in this experiment, it took, so we used 5.6 million samples in total, and for each MCMC sequence, it took 1.8 hours, and we needed 14 MCM Markov chains for numerical integrations, and in total we got 25 hours. On the other hand, in our approach, we have to train the deep generative models, normalizing flows, which took 20 hours. But the sampling is very fast, less than 1 minute. And so in this experiment, basically, we somehow chose the situation where our method is a bit faster and more accurate. But basically, because sampling from normalizing flow is very fast, so our approach is good when more accuracy is necessary, because we can easily increase the number of samples. And then in this situation, the training time is less dominant, and our approach is more advantageous.
Can I ask a question? So, how about the memory usage? You need to maintain the trained model to sample from the distribution.
Yes. Okay, memory. So if we compare with MCMC sampling, it's huge difference. But basically, we use.
Did you use a huge model in this experiment?
So it depends on the lattice size. Basically, the lattice size should be increased, but I mean, we don't. Okay, we actually computed 64 times 8 lattice, and okay, I don't recall the detail, but I mean, we use more complex models with more layers, and but basically we do what our cluster computer allows.
Okay. Yeah, thank you very much.
So before we go to the next topic, if there's any question, I will answer. If not, I'll move to the third topic, which is actually short. So this is about mod clubs. So this slide I already showed, and this is about the importance sampling. And this slide explains how to estimate the observable with importance sampling. And I said QS needs to be accessible, but there's another important condition. So the model support must cover the target support, and this doesn't always happen, and this can be a big problem. So in this fit to the power of fourth theory, there is a G2 symmetry, meaning that if we change the sign of the field, the action is the same. Okay. Yes, the action is the same. And in this situation, okay, so I will talk about how to train this model, but typically we train the model by minimizing this scale divergence. And actually, this is convenient to use, but this can cause mode dropping. And in this part, I don't talk about the training, but I just assume there are trained model with mode clubs, and the one without mode clubs, and how to detect mode clubs. So let's say we have two models trained, and the yellow is the properly trained model, which we say mode covering model, and the purple has mode clubs. And in the previous part, I talked about how to estimate the partition function Z, and we name it reverse Z estimator, and we define this estimator as ZQ because we draw samples from the generative models, and because this this partition function estimator draws samples from Q. So if the Q has mode collapsion and like this purple, we never get a sample in the left-hand side. So basically, this estimator ignores the dropped mode, and it just gives some value. And if we only see ZQ, we are not aware of mode collapse happened. And to detect mode collapse, we proposed another estimator, which we call forward Z estimator. So this estimator can be similarly derived in this way. And we name it ZP because here we draw samples from the Boltzmann distribution. So when this means that when we use this forward Z estimator, we need to use MCMC sampling to draw the samples from the Boltzmann distribution. And but here, please note that this is different from the standard MCMC sampling method to estimate the free energy, which requires numerical integration from kappa 0 to the target value. But we can just apply. We can just get the sample MCMC samples at the target system, and we can estimate this value much faster than the standard way of estimating free energy. And actually, we have these two estimators, and they should match if there's no mode collapse. But if there's mode collapse, or more generally, assume that the support of Q and the support of P are not the same. So in this case, we have these inequalities depending on the support, like this. And actually, we can get this result. So basically, D is the true partition function, and the expectation value of ZQ and the expectation value of ZP are lower and upper bounds of the true partition function. And if the support of the model covers the Boltzmann distribution, the equation holds, and the other way also holds. So we have this relation, and we tested these estimators in our experiment, and we found that the equality it was validated, and if the generative models doesn't have mode collapse, the two estimator matches, and if not, we have a big gap. So basically, by checking these two bounds, and if the gap is large, there's a possibility that mode dropping happens, and also because P is Boltzmann distribution, and theoretically the support is covers the whole space. So in this sense, ZP or forward Z estimator tends to robust. So by using these properties, we can detect mode dropping, and also if we want to robustly estimate the free energy, it's better to use DP or forward Z estimator. So this is the second topic. Again, if any question, I will answer, and otherwise I'll go to the last topic?
I was a bit lost in the last slide.
Okay.
You could detect the mode dropping, but how do you correct it?
Okay, so here I would say ZP is basically always good because P is the Boltzmann distribution with infinite support, and then the latter always hold. So ZP is basically unbiased.
So in terms of mode dropping, what do you mean by that?
In terms of mode dropping.
Even if the mode is dropped?
So if there's mode dropping, the support of Q shrinks. But the latter equation doesn't matter.
I see.
But I mean, of course, practically, there is a very low density area for P, and practically maybe we shouldn't too much rely on this relation. But I would say ZP is more robust.
That's my second question. So
Okay.
how about the efficiency of the estimation? Being robust often means less efficient.
Okay. Here we need MCMC samples, and as I explain here, it's faster than the standard way of estimating the free energy, but here. So standard MCMC sampling, we need to perform the whole numerical integration up to, let's say, here. And on the other hand, the estimator ZP or forward Z estimator, we only do MCMC samples here. So in this sense, I mean, in this particular setting, 10 times faster than the standard method.
I see.
If no other question, I'll go to the last part. So it's about the path gradients for training normalized flow with reverse and forward Kullback-Leibler divergence. So as I said, compared to the standard MCMC sampling, our approach has a bottleneck of training time, which typically dominates the computation cost. And we are trying to reduce this computational cost. And before I go to the detail, let me talk about the forward KL and the reverse KL. So they are just difference in the order of the target Boltzmann distribution and the model distribution. And both quantities are used for training normalizing flows or other generative models. And let's think about forward KL first. So in the forward KL, if at least if we do form naively the estimator, we require the sample from the training distribution. And this situation typically happens when we want to train generative models on the huge training data like ImageNet or this kind of computer vision applications. So basically, we are already given samples from the true distribution, then we can just minimize the fourth KL, which corresponds to the maximum likelihood learning, and this is very popular. And on the other hand, reverse KL is also popular in under some situations. So the goodness of this reverse KL is that we can sample from the model. So as long as we use efficient generative model, which allows efficient sampling, then it's very handy to use. And this method is typically used when we are not given the samples from the true distribution, but the unnormalized true distribution. And this is typical in when we do Bayesian learning, and also our application with Boltzmann distribution. So we are given unnormalized target distribution. So actually using reverse scale is very convenient. Okay, so sorry for the interruption. So I continue. Yes, so this reverse scale divergence is often used in Bayesian learning and about in our application as well, because we are given unnormalized target distribution.
So I'm a bit confused here. So Q of P is the model you are approximating to distribution.
Yes.
And what was P tilde?
P tilde is unnormalized target distributions. For example, in the Bayesian learning, it's a posterior distribution. And typically we are given unnormalized posterior distribution, which is joint distribution.
But you need to have the posterior, unnormalized posterior in an explicit closed form.
Yes, at least this, in this straightforward procedure, it is required.
So the reverse scale is not always available in practice.
Yes, but yes, I mean, I'm Bayesian, so it's often available. So in Bayesian learning, it's often available.
No, I mean, if the posterior cannot be computed explicitly, like only sampling is possible.
The true posterior is not accessible.
The likelihood function is so complex.
Yes, in that case, but the likelihood function is known, or
so suppose it's known.
Known, but
then still you can compute it. So because it can be unnormalized, so it's just a product of likelihood and prior.
Yes. So I think in most applications, whether we are given data or we are given unnormalized distribution.
Okay.
If we are given data, people typically use for KL, and I mean, in Bayesian learning, of course, data is given, but this data is not the sample from the posterior distribution, and we are just given unnormalized posterior distribution without any sample from posterior distribution. So in that case, reverse scale is very handy. Okay, and now I'll talk about so-called path gradient. So we think about training normalizing flow, as I already said. And here, G corresponds to the bijective mapping between the data and the latent space. And let's think about training normalizing flow by minimizing the reverse scale divergence. And we can, of course, compute the scale divergence up to constant, and we can apply autograd, and then we get the gradient of the scale divergence, which we call total gradient. And actually, we can, in a natural way, decompose into two terms, path gradient and partial gradient. The partial gradient is often called score gradient. And the path gradient, if you see the magenta circle, so G of Z corresponds to X. So basically, this is the contribution from the chain rule through the X. And for this reason, it's called path gradient. And the partial gradient is the direct contribution of the form of the model Q. And we can get some estimator in a straightforward way like this. And here there's interesting property we can get. So the first of all, the partial gradient part, the last part, the expectation value of this estimator is always 0, we can show. And also when Q is close to P, meaning that the training is in the converging phase, then the variance of the path gradient, okay, sorry. So I said variance, but this is covariance. Covariance of the path gradient estimator converges to 0, while the covariance of the partial gradient converges to some finite value related to the Fisher information. So this means that this partial gradient part, the expectation value is 0, meaning that there's no information. And the variance is finite. So meaning that this just produces noise in the converging phase. So then it's better to ignore this part, which was found and proposed by Rader in 2017. And we can apply this idea to the normalizing flow. And how to implement it is also quite easy. We basically should use the stop gradient or detaching in the process of objective computation and use autograd. Then with this, actually this trick is quite simple. And with this simple trick, we get better convergence of the model. And here the figure shows the forward effective sample size, which I will explain later in detail, but now it's just a measure of the goodness of the generative model. And the horizontal axis corresponds to the lattice size of our lattice field theory. And we see a big gain by using path gradient compared to the total gradient. And we now, from now on, we also worry about mode collapse and think about using forward KL training. So in the previous part, I explained how to train the model by using reverse KL. And as I already said, this is used because it's very convenient to use in our application. But there's a property of this scale divergence, which is that this value is large if px is very small for some at some x such that we can get some sample. So because p is in the denominator, so if we get sample from q, which gives very small p, then this objective function is very large. And we can, of course, think about Ford KL, and similar property or opposite property we can observe. And this result in this property. So we can say Ford KL, the left-hand side, tends to do mode covering because of this property, and the reverse KL tends to cause mode seeking or mode dropping. And in our application, as I said, mode collapse is very harmful because it makes the observable estimator unbiased. But the mode covering is not a big problem because we apply importance sampling. So mode covering property just reduce the efficiency in terms of the variance, but it's not very critical. So this motivates us to use Ford KL to train the normalizing flow. And let's think about training with Ford KL divergence. And we basically compute the Ford KL divergence by using importance weighting. We see the importance weight here, and we switch the sample from the model. And in the last equation, we just use reparameterization expression, and this is the gradient estimator, original gradient estimator. And here it's a bit different from the reverse scale case where we have a total gradient here, but now we have partial gradient here. And so the original gradient estimator is the partial gradient, and we can somehow apply the similar trick by using the relation between total gradient, path gradient, and partial gradient. So here, partial gradient can be expressed by the difference between total gradient and path gradient. And we can get corresponding estimator. Here, there is a little bit of complication because we need to estimate the partition function. So it's a little bit complicated, but this is our natural way to form estimator. And actually here we get some similar property as before. So we can show that the total gradient is always 0. And when the model is close to the target distribution, the covariance of the path gradient estimator converges to 0, while the covariance of the total gradient estimator converges to some finite value.
Can I ask a question here?
Yes.
So I think the ratio of density P divided by Q theta, this may be estimated accurately or in an unbiased way. But how about its derivative? Can you say that your gradient estimator is close to the true one?
Actually, we have two versions of this, and this version we estimate the partition function, but we don't take the derivative. So in this sense, it's I mean, d hat itself is unbiased, but actually we don't take the derivative, but we take 1 over z hat So in this sense, there should be some bias actually, but we somehow ignore.
I was asking this because previously actually I worked on estimation of the gradient of Kullback-Leibler divergence or something like that. In that case, actually estimating the Kullback-Leibler is not really good, but estimating the derivative of Kullback-Leibler directly makes actually more sense.
Oh, okay. So, but maybe this corresponds to the case. So, basically, I just derived the derivative and the.
But in your case, so first density is estimated and its derivative is computed. Then already the final accuracy is not guaranteed at all.
Okay, so you mean the derivative itself is modeled.
Right.
Okay.
So then the smaller error directly means the smaller error in derivative estimation. But if your density estimation is quite good, but still it can be extremely fluctuated, then the derivative estimation error could be unbounded. That's a potential, I think, error.
Okay, but this derivative is with respect to the parameter. So our goal is density estimation, and we need to train it, and we need to compute the derivative of the parameter. But as long as I remember, your case is like you're interested in the derivative
of the
with
density.
respect to the position variable.
Okay.
But there should be some unbiasedness issue for the gradient estimator, I guess. But for now, we don't care much. Okay, so now we found that total gradient is 0, but the variance is large. So then, as before, let's just ignore this, and we actually get better performance than the original partial gradient estimator. Okay, so this is just a slide with 2 experimental results, which I already showed, and so this is the last part, and then I will talk about what is forward effective sample size, which is used as the measure of the goodness of the generative model. So before this, I will explain what is effective sample size. So we are basically using importance sampling estimator, which has the self-normalized importance weight. And when we do estimation, we are interested in its bias and the variance. And they assume that the model support covers the target support. Then, as I explained in the beginning, the mean of the importance sampling estimator is equal to the target value plus small o1, meaning that it's asymptotically unbiased. And we can compute the variance of the estimator by using central limit theorem in the limit of large sample size, and this variance can be expressed as the variance of a single sample estimator divided by some factor, which is called N effective. And the N effective can be estimated by this equation, where W is the importance weight. And this is called effective sample size because, first of all, if P is equal to Q over all the input space, then this value is equal to the sample size. And this means that we can use the whole sample as IRD sample from the data distribution, and as in the typical case in statistics, the variance is inverse proportional to this value. And when P and Q doesn't match, N decreases. And this somehow express the efficiency of importance sampling. And this efficiency is represented by effective sample size, this NEFF. And here we again name it reverse effective sample size, because here when we compute the denominator of effective sample size, we draw samples from Q. But this, in a similar way as before, we can change the expectation, the distribution for expectation to the Boltzmann distribution by removing one factor of importance weight, which we call forward effective sample size. And before this, so if there is no mode class, both effective sample size should match, because this equation should hold. And but if there is mode dropping, then this forward effective sample size, this denominator can diverge, because we get some sample from P, which can make the denominator of W 0. So then if there's mode dropping, basically this forward effective sample size goes to 0. And so in this sense, forward effective sample size is sensitive to the mode dropping, and it can detect the mode dropping and reduce further the effective sample size. And this value we use for evaluating the generative models, and we get this result. And this table summarizes forward effective sample size and reverse effective sample size. And we compared different gradient estimators and plotted the trained model. So rainforest is the very traditional gradient for training normalizing flow. And we have forward KL with path gradient, and the reverse KL with total and path gradient. And actually, we tested two versions of path gradient of forward KL, which is a very tiny difference. So I omit this part, but basically both estimators works better than the others. So in summary, we can say path gradient of forward Kalbach Leibler divergence performed the others in training normalizing flow in our case. Okay, so this is the end of my talk. So I first introduced our approach of importance sampling for Monte Carlo simulation, and how to get unbiased estimator. And I explained about our applications in lattice field theory, and to estimate the thermodynamic observables like free energy and entropy. And I explained how to cope with mode collapse by using bounds of that. And I introduced our work to use path gradients for forward and the reverse KL divergence to improve the final model performance. And although I don't talk about it, but we extended our work to continuous normalizing flow, which get popular, and the process is a little bit complicated, but we derived path gradient for training continuous normalizing flow with reverse and forward care. So this is the end of my talk. Thank you for your attention.
Okay, thank you very much. So then now it's time for question and answering. So let me start. So yeah, thanks for the nice talk. So in ordinary importance sampling research, I think the reduction of the variance is the main interest in many cases. But in your line of research, do you need to also discuss such an issue?
So reduction of
the variance of the importance estimate. Because the naive one is unbiased, but it has a huge variance usually. Not that useful in practice, like in the case of reinforcement learning.
Mm-hmm.
So in your case, isn't that a problem? As long as you have a large number of samples, maybe it's not a big issue. But if the system is high dimensional, then always you need more samples.
I think it depends on the quality. So if you are talking about the importance sampling of the Monte Carlo simulation itself, or training?
My case is more like estimation of something from training data. Then the number of samples is always limited. That's why the estimation variance is quite important.
Okay.
But in your case, it's MCMC and you can generate as many samples as you want.
Yes, basically, I mean, linear computation time gives. And also, like, if the variance is too large, we just retrain better model for Q, so that W is always close to 1.
I see.
But I mean, of course, if we use better importance weight, but in that case, there is bias. So
yeah, usually we add small bias to reduce the variance significantly.
And but can you estimate the bias?
It's more like regularization. Just add small bias.
Okay, so I think for this particular application, having bias is very critical because I mean, physicists cannot conclude. I mean, within this range, the true value should be there or something they need to claim. But I mean, if we can estimate, for example, upper bound of the bias or something, then we can still.
Or at least you can easily like have a kind of adaptive regularization. If you have more samples, the amount of regularization is getting weaker.
Okay.
Like we may consider squared error instead. See the bias and variance, squared bias and variance.
Okay, I think so. I haven't thought of it deeply, but maybe there would be some way to use it in some situation.
But at least in your case, the number of samples is not small, so you can generate as many samples as you want.
Yes,
so
because
maybe the variance reduction is not a critical issue.
It comes from our model. So
I see. Thank you. So then, any other questions? If there's no further question, then let's conclude the seminar today. So please join me to thank Shin again.
Thank you very much.